This is why we're very excited.
Yeah.
Because we get structure formation, galaxies, galaxy clusters, the CMB, potentially dark matter, all of this for free, just by putting a hat. And the problem that we wanted to solve was something else. It was a horizon problem. We wanted to explain why the universe was homogeneous. Instead, we found a mechanism to explain why the universe has structure. The skeptic would say, okay, how can you really prove to me that this is quantum?
Yeah.
We're stuck. We don't know how to do this, but there are a couple of proposals and there are a couple of difficulties. Proving that the inflaton, which is this field, is quantum will be a major step towards saying that gravity itself is also quantum. We have one universe, we have one detector, we don't have the copy as we would in the lab, which is why it's very difficult to do a Bell test in cosmology. Think of a temporal Bell inequality, not a spatial Bell inequality. Can we measure the system twice instead of measuring two different systems at the same time? You can never access this on a ground-based experiment, but the universe has done the experiment for you. Your detector is more quantum than the system itself, which has never happened in the laboratory. The notion of what it means to be vacuum changes as the universe expands. You can just think of it as a clock that runs so slowly that it feels like infinite time has passed. Between 0 and negative infinity, the edges of the universe are expanding faster than light itself. Even if it's a tiny bit, it's a little bit, that's exciting. That would tell us that gravity is quantum. Let's look at one particle in the condensate. This is a creation operator. If I act on the vacuum state, I will get one particle. You can keep doing that as long as you like. We haven't done any quantum mechanics so far.
And it's still really cool.
It's still really cool. When quantum mechanics comes in, it becomes cool. Keep trying. We'll prove that gravity is quantum eventually.
My brain is now in the shape of the negatively curved universe. Hello, welcome back to the Quantum Foundations podcast. I'm Maria Villores.
And I'm Aditya.
And today's episode is about how quantum mechanics meets gravity and some aspects of cosmology. Now, if you've watched previous episodes of the Quantum Foundations podcast, you'll know that there's two branches to it. One is an accessible version and one is a mathematical version. This is the mathematical episode with Aditya. And Aditya is a postdoc at the University of Oxford in the group of Vladko Vedral, which is also where I did my PhD. So thanks for joining us today,
Thank
Aditya.
you for having me.
And we will, if people want to watch the accessible version, it is already on YouTube, so you can watch the previous episode if you like. And today's episode will be kind of assuming that you have some introductory background to quantum mechanics already and the mathematical formalism. So hope you enjoy.
Yeah.
So to get started, could you tell us a bit about what you did in your PhD?
Yeah. I worked on the frontiers of quantum gravity and cosmology, so in between sort of the low energy realization of tests for quantum gravity in lab-based experiments and potentially extending some of that logic and the results we had to high energy, which is cosmology. It involved a bunch of experimental proposals, ideas on what we could see as potential signatures. In fact, my PhD thesis is called Signatures of Quantum Gravity. It's an assortment of topics all the way from lab experiments to black holes and cosmological signatures eventually.
Mm-hmm. Cool. And maybe you can tell us a bit about what these thought experiments or experimental proposals are?
Yeah. Let's start with, I guess, the simplest one, which is the BMV proposal, which you might have discussed in the podcast before. Essentially, it's this idea that you have a gravitational field. Let's denote this as the z-axis, and there's a gravitational field acting in this direction. You could have a mass that's at this height, and you could have another mass at this height. So let's call this h1 and h2. Because the acceleration due to gravity is the same, and the heights are different, they pick up different potential energies if you place a mass there. And as you know, the Hamiltonian is a generator of the energy, so this means this should be picking up a phase, e to the iht. Let's call it state of the mass psi. So if it's at height h1, it picks up a phase, that's roughly mg h1t, where g is the acceleration due to gravity, and h1 is the height, and h2 would be h2. We could just replace it like that. So this was an experimental proposal that Feynman conceived very early on in the Chapel Hill conference to say that if you could superpose a mass at two different heights, h1 and h2, and do a full interference experiment, there could be a way that we could prove that gravity is quantum. You could say that we've essentially interfered the mass and the phase was a result of the gravitational field, therefore it must have something to do with the quantum nature of gravity. But as I've just shown you, this actually has nothing to do with the gravitational field. It's just a phase that it picks up by virtue of being at two different heights. So my supervisor Vlatko and Chiara Marletto, along with Bose, an independent realization, came up with the idea that why don't you do this with two masses instead of one? Let's call this M1 and M2. And we know that this gravitational attraction, the nature of which is unknown, it could be, let's call this G, for example. It could be a quantum field, or it could be a classical field. And the idea is to propose an experiment that can tell you whether it's quantum or whether it's classical. The amazing idea behind this is similar to Feynman. You could put this mass in a superposition of two locations and this mass in a superposition of two locations as well. And what that would mean is, depending on where the mass is, which branch of the superposition it's in, let's call this branch 0, which I will denote by ket 0, and we call this branch 1, 0, 1. Again, the gravitational phase that these masses pick up would be different depending on the branch of the superposition we're in. Did I get all of them? I think I missed one. This one. No.
The first of the last.
Yes.
Yeah.
Right. So you have four different phases that are picked up depending on which branch of the superposition the masses are in. What that means is you can write a combined state that looks like, we can separate into two parts. Let's call this mass 1, 0 plus e to the I phi 1, which is a phase 1, and then you call this mass 1, again 0 e to the I phi 1 plus some delta phi, which we shall denote like this. So this is the phase difference. That's a result of the masses being at two different positions. So we can denote the distance between these two, between 0 and 1, to always be d1, and we'll say 1 and 1, which is, apologies for all the arrows, viewers.
I think we might just be going off screen.
Okay.
No, I think it's just about okay.
Okay, so that's
Yeah.
d2, which in these phases, as we've just shown here, are related to the degree of separation. Except in this case, we have the interaction time, which is of the form gm1 and 2 divided by d, where d is the separation between the two masses. So depending on which branch of the superposition the combined state of the mass is in, you would pick up various phases that are mediated by gravity. Now we still don't know whether this gravity is quantum or classical. Sorry,
So here so just to recap, we've got two masses, put them each in superposition, and then we have four different gravitational attractions between the masses in the four branches of the overall superposition that has now been created. And that's represented here by the terms being 0, 0. We've kind of set it as not having picked up a phase. Because there's one global phase that you can always pick out. So I've just done that so that we don't need to see four different numbers on this on the blackboard. So you've abstracted out this global phase so that this one doesn't have a phase. Then you have this phi 1 is set by the distance between one of the zeros and ones. So this pair, I guess. And this is set between the other pair? So it does look confusing in this diagram, but if you imagine a more parallel setup and makes a symmetry argument, why should the masses be distinguishable? It stands to reason that the phase should be the same in 1, 0 and 0, 1 as well. Right. And then we have this delta phi is on the 1-1 term.
Yeah.
So that's set by this.
Yes.
The distance between
Yeah.
those masses.
Yeah, so essentially the idea is they all pick up different phases,
Mm-hmm.
and because they did pick up different phases, it's now possible to do an interference experiment with the two masses. So you can imagine a setup where you have a mass that starts off in this here and here, and this mass goes through a beam splitter. So this is our beam splitter. It goes like this, and you create a superposition, and this is a mirror here. This is in state 1, state 0, state 1, state 0, and then you put another mirror here, get them to combine, and then you do a detection, essentially, with the detector.
Mm-hmm.
Now, depending on the phases that they pick up, and due to the mutual gravitational interaction between the masses, the probability that they appear at a particular detector would be different. And you can vary this by setting the parameters of the experiments. If you vary the length of the interferometer, it's going to be different. If you vary the separations, which is D1 and D2, it would be different as well. So you can tweak these to get a signal. Now the brilliant idea behind this experiment is that this is not pure state. It's not just doing interference of a single mass, it's actually doing interference of an entangled state.
Mm-hmm.
And the idea is, if our two masses started off initially as disentangled, unentangled states, and the only thing that they used to interact with each other was a field, gravity, which we don't know is classical or quantum, and somehow these disentangled masses were able to interfere such that an entangled state would. And we saw that the interference pattern is different from an unentangled state. We could conclude that the field that mediated the interaction must be quantum, because how else would a pure state that doesn't interact with anything else become an entangled state? And if you'd like to see this in more detail, we could first erase maybe this. We could get rid of this. We could say something along the lines of, if I had qubit 1 plus a mediator, let me call it G, if it were classical, the only states it could evolve into are of the form identity, which means nothing happened, plus rotation on one of the qubits. So let me call this, I believe in the paper they use R to represent a rotation on the qubit.
Mm-hmm.
So here Q, this might be slightly different from what you're used to seeing in your normal quantum mechanical courses. It's any qubit can be represented on a block sphere by its descriptors, which we call sigma x, y, and z. So this is just a rotation of that qubit on that block sphere, and then we have S acting on the classical qubit. So let's call it little g, I guess. Not to confuse you with the acceleration, so let's call it gr. It's a little, it's a classical, if it's a classical mediator, it would have only 1 degree of freedom, which means it either points up or down like a bit. It can't rotate around the block sphere like a qubit would. So this is something corresponding to the flip. And then you have another term, which looks like this, essentially. Sorry, yeah. So this is not an entangled state.
So this is representing the quantum and classical parts. And can you say again how the classical part is being represented?
Yeah.
Mm-hmm.
So here we have the combined state of one of the qubits and the mediator. We still don't know if the mediator is quantum or
Right,
classical.
so it's an unknown
It's
mediator.
an unknown, yes.
Mm-hmm.
And the argument we're trying to make is, let's assume that the mediator is classical, so I'll put a little c here.
Mm-hmm.
If it were classical, the only state that the qubit in the combined system can take is denoted by this expression. It is the most general possible state you can have if a classical field interacts with the quantum qubit.
Right. So with classical meaning that you can only bit flip.
You can only bit flip, yes.
Then this is the most general way to represent this combined state.
Exactly. But our state, so if you, this is for 1 qubit, and the gravitational field, of course, we're talking about 1 more qubit, so let's call it Q2, qubit 2. It's going to be a bit more ugly, but if you look at it properly, you'll see that it can't be entangled because the bit is classical. The gravitational field is classical. So that's what this experiment tries to show. It tries to say if you have a classical mediator, there is no way your 2 masses can be entangled at the end of the experiment. But if you have a quantum mediator, then there is a possibility that you can explain why the masses you saw at the end of your interference experiment are quantum. This is one of the most elegant tabletop proposals, which our supervisors proposed even before we joined the group. And a lot of my PhD thesis is developing this line of thinking, both in the laboratory as well as in high energy physics. Yeah.
Cool, great. And some of the ways that you've been thinking about this or modifications of it have involved Bose-Einstein quantum states?
Yes, so if we can get rid of this. So some might say the difficulty in implementing the BMV experiment, which is the experiment that we just spoke about, is that you need access to 2 masses. Putting 1 mass in a superposition is hard enough. Now you need to put 2, and then you need to ensure that they only interact through gravity, nothing else, and then conduct this very careful interference experiment to get an outcome. And there are some brilliant proposals that actually do that. But we started thinking, is there a way that we can use a single mass and a different witness besides entanglement that could tell us that a self-gravitating mass would show a different value in whatever witness that is, which I'll tell you about, depending on if it were gravitating with a quantum gravitational field or classical gravity. So that's the experiment that we did in the lab, that we proposed, and it was with a BEC, because BECs, as you know, are quantum systems. And yeah, it's an elegant proposal. I'd like to tell you a little bit about it. So the reasoning goes as follows. Let's say we have a condensate, which is this object here. It's made up of many particles. So for simplicity, let's look at 1 particle in the condensate. So if this is a creation operator, what this means is if I act on the vacuum state, I will get 1 particle. And you can keep doing that as long as you like. If I do it once more, I would get another particle, and so on and so forth. So that's how I can create many particles for my BEC. Now, from Newton's laws, again, we're going to work in the Newtonian regime, as we did in the BMV experiment. We know that the gravitational interaction between 2 masses, and the gravitational potential energy of a system of 2 masses is like this. And in the continuous limit, if you have a distribution of mass, which we'll call rho r, is the density distribution of the masses, and phi r, this would give you the potential energy of the system, essentially, which we shall call h, the Hamiltonian. Now, there are 2 ways of doing this. The first way is to say, I'm going to treat my matter. This is matter, and this is to do with the gravitational field. I'm going to treat this as quantum, and this is classical, similar to the BMV experiment. Or the alternative is, I'm going to treat this as quantum, and this is quantum as well. I think since we're doing this podcast, we have no doubt that matter is quantum, because this table is quantum, as we know. So now the idea is, if this self-gravitating mass, a BEC, were to gravitate classically, the only term you would see in your interaction is of the form A dagger A, where you create this is the number operator for a particle, and some averaged value of the potential what does that mean? So this is the classical case. So we'll call this H classical. The interaction Hamiltonian in the classical case would look like this, where this is just some expectation value, and you can think of it as the state of the condensate, and you're just taking the sandwich of the potential. Whereas if you have a quantum Hamiltonian, you have to treat every mass in your system as quantum. You don't have the luxury of doing this expectation value. So what that means is you would have A dagger A plus B dagger B, for example, for the rest of the condensate.
So that's how you're treating the
classical
condensate
versus the quantum
as
state.
quantum.
Yes.
Right.
So in this particular case, we took the expectation value over the distribution of the condensate and called that the semi-classical gravitational field. Whereas in the second example, we said, no, we're not allowed to do that. I'm not just going to quantize this, which is the A dagger A that you see here.
Yeah.
So that's A dagger A. I'm going to quantize this as well. Why shouldn't I? Because both M1 and M2 are equally quantum. So we get another B dagger B, if you want to call it. But since these are identical particles, you can just think of it as another A dagger A. It's a BEC. They're all identical particles. So you're just creating many of the same particles. So there's a very critical difference between the term that you see here and the term that you see here. And I'm just gonna, for the sake of being proper, I'll put these two dots. This means normal ordering, and that becomes important later because these operators don't commute. So we have to be careful with the way we write this down. But for illustrative purposes, you have a quartic term and you have a quadratic term here.
Right.
What that means is, if you were to use a certain witness called non-Gaussianity, the classical Hamiltonian will not generate any non-Gaussianity, whereas the quantum Hamiltonian would generate non-Gaussianity. And what is non-Gaussianity exactly? If you construct the Wigner function of this state, let's say the state psi, the Wigner function is kind of a mapping, a desperate way to map a quantum system into phase space. It's a quasi-probability distribution, where the probability distribution can take negative values. We've not seen negative probabilities in classical phase space, so the argument that Wigner and a few others, Weyl and a few others made in the 1950s was, if the Wigner function has a negative probability, it must mean it's describing a quantum system. Now,
Right.
Yeah.
So this function is a signature for something being quantum.
Yes, so if the function takes negative values, it's a signature that the thing the function is trying to describe is a quantum system, which is what we're trying to show here. We're trying to say, let me model the evolution of this system under this Hamiltonian, this system, the BEC, under this Hamiltonian and this Hamiltonian. I will plot the Wigner function in both cases. If, say in this case, there's no negativity, then it's confirmed that it's classical. Whereas in this case, if there's some negativity, I would say that the interaction is quantum. Therefore, the field mediating the interaction, again, gravity, is quantum, thanks to that witness having certain properties. If you actually do the evolution, let's say you start off with your BEC in a nice disciplined state. It has a very narrow spread around position. The wave function of the BEC is like this. If you evolve it under this Hamiltonian, it just spreads a little more, and the Wigner function looks like this, which is a Gaussian function. Has a nice mean, a nice standard deviation. But if you evolve it under this, the Wigner function does not look like this anymore. And it looks a bit like this. Now, this is a three-dimensional system, and I'm trying to draw a 3D system with a line. Well, actually, it should look, if you rotate this thing around itself, you will get the Wigner function in all the coordinates. Notice that this is not the Gaussian state that your condensate started off in. So if you notice this Wigner function, if you computed it after doing the experiment many times with your BEC, again, only interacting with gravity and nothing, self-gravitating, nothing else, and you observe that the Wigner function is non-Gaussian, then you could say that the self-gravity, the gravitational field, is quantum. So we did this with one mass,
Right.
1 BC.
Yeah.
To tell you like how much of this you need maybe 10 to the 9 atoms of cesium. The width of this BC would be roughly 200 micrometers, and you need to let it evolve for around 2 seconds before you can see it transition from this state to this state. It's a pretty
Right.
neat experiment that you can do
Yeah.
in the laboratory.
Right.
Yeah.
Cool. And so you kind of figured out these parameters that would be needed to do it, and you found these kind of values, and are these close to what people can do?
Yeah, so the idea of these parameters is to say, if I go and measure these in the lab, can I see them?
Yeah.
I mean, theoretical physics does not care about what values these parameters are. We just care about the signal. But
Yeah.
for experimentalists,
Yeah.
and for any verification, really, we need to be able to observe it in the lab.
Mhm.
And for the limits that we can observe right now, this particular choice of parameters would lead us to observing the non-Gaussianity in the lab, and we're not quite far away from it. Problems, however, are a BEC is not just a gravitating system. It has atoms. So there are electromagnetic interactions, dipole-dipole interactions, van der Waals forces, the huge zoo of forces
Yeah.
acting there. So how do we distinguish between the same kind of quartic term that comes from those forces versus what gravity gives us? And thanks to advancements in experiments, we can filter out most of these things by applying an external magnetic field. So that sort of suppresses the electromagnetic interactions, and the hope is that you're left with only gravity. And within the error limits to which we can suppress the force and the signal that we want to see, it seems like with this choice of parameters, we should be able to see this in an experiment fairly soon.
Cool. And people are working on this type of experiment.
Absolutely. I mean, it's inspired by BMV, which was one of the first experimental proposals of its kind. It started off a whole new wave of proposals, one of which is this.
Yeah. And how would you see this one? How does it compare to BMV? Like, is there a difference in terms of the conclusions that you draw about gravity from it?
No. So the nature, again, we're only interested in saying is gravity classical or quantum. And I think both the BMV experiment and this experiment, if you just look at them as qualitative tests, not the extent of the signal, let's forget about the extent of non-Gaussianity we have. Even if it's a tiny bit, even if it's just like this little bit, that's exciting. That would tell us that gravity is quantum. But one of the advantages of this experiment is, because you're working with a single mass, you don't need to belabor yourself with doing it for 2 masses. And there's another thing called the signal-to-noise ratio, which scales as square root of m for this experiment. So it's a slightly better property. You need to do fewer experiments of this to get that signal that you're looking for. So that's what we did. About 3 years ago, the paper's out there to read, and we're very excited about somebody actually being able to implement this.
Cool. Yeah, very nice.
Yeah.
Cool. So maybe now we can talk about some other thought experiments related to gravity, or we could think more about the cosmology side that we also talked about in our previous discussion. We talked about things like the vacuum fluctuations and how quantum mechanics comes into that, and in the early universe. So could you tell us a bit about those cosmological considerations?
Yeah, absolutely. I think that's where we really go from low energy physics like this to high energies. Now we understand most things about the universe up to about 1, maybe even 10 tera-electron volts really well. This is the energy scale that's been mapped out by the Large Hadron Collider. It basically circulates protons at that energy scale, and we can understand pretty much anything at those energy scales. But when you go earlier and earlier, when you go into the early universe, the energies become very high. So to give you a flavor, it's of the order 10 to the 19 GeV, could even be higher, and we're in the realm of something else. These are energy scales that are not very well known, but our universe has existed in these energy scales. So trying to map out if these high energies could give us some signatures of quantum gravity, and where you can never access this on a ground-based experiment, but the universe has done the experiment for you. Can we observe some of that? It's kind of a difficult area to be in, but there are some promising signals that we can talk about.
Yeah. So this is more, maybe more ambitious than the kind of tabletop proposals, which are more tangible in
absolutely. Yeah. And what I'm going to talk about is actually not the only kind of experiments people do out there. There are many exotic astrophysical objects, like gamma ray bursts, active galactic nuclei. These things emit radiation all the time, like gamma rays, a huge flux of neutrinos. Sometimes it might even be worth asking, how are these particles that are emitted by such massive objects going to curve, for example? Does that have something to do with quantum gravity? And this is a whole branch of physics that's now being pursued by astrophysicists and cosmologists. And then there's the other type, which is what we're going to talk about today. We have a CMB, a cosmic microwave diagram, which, if you think of this as the map of, I wish I had a picture, it's much more beautiful than this.
So beautiful, or inspiring. Yeah.
Look it up, it's very nice. But if this is the map of the whole sky that we can see, the map of our universe, it has these little speckles on it. And these little speckles are nothing but variations in temperature of the sky. So the CMB is roughly around 2.7 Kelvin, and it fluctuates of the order 10 to the negative 5. So 2.7 followed by so many zeros, 1 for example, is the order of these fluctuations. And now, one of the things that we're going to be talking about is how these fluctuations could have been seeded by a quantum field, a mysterious. So before I sell you too much on this theory, I'd like to say that it's a mysterious field, phi, and we've never seen anything like this in our lives. It's completely theoretical, which is why we don't even call this a theorem, or theory rather, we call this a paradigm. Right. And this is the inflationary paradigm, which is supposed to give us the mechanism for how these structures were seeded. But before we get into that, this was actually a bonus of subscribing to the inflationary paradigm. This was not why it was invented. This just came out as a consequence of another problem that we were trying to solve. So that takes us into classical cosmology for a little bit. So we'll talk about some problems that faced classical cosmology, which led people to propose the inflationary paradigm in the first place. And eventually what happens when you quantize this field phi, you put a little hat on it, it gives us all this structure for free, which is what excites us a lot as physicists who have worked on this theory. But it's by no means a proven theory. It's just a very elegant theory waiting to be tested. So going back, we all know from special relativity that you can do this. This is how we add space and time. You have a metric tensor that combines space and time to give you the notion of a proper distance. But when you're in cosmology, you're working in the realm of general relativity. It's no longer just space and time interacting this way. So what you have is a more complex metric, which looks like this. I'll explain what all of this is. I usually get some of these wrong. Okay, I think this is it. So this is the Friedman-Robertson-Walker metric. It's the metric of cosmology. This is only telling us that the universe is homogeneous and isotropic, which means if I look at the universe this way or that way, it's homogeneous, it's the same, translationary invariant. Or if I look at it in all possible directions, if I do this, if I look here, in all these radial directions as well, the universe is the same, so it's isotropic as well.
Right.
So that structure, the homogeneity and the isotropy of the universe, is encoded in this metric. There's one free parameter here called k, which, depending on if k is 0, -1 or 1, we say the universe is flat. The universe is negatively curved, and the universe is positively curved. a flat universe is very easy to imagine. It's just like this blackboard, nothing interesting going on. A positively curved universe is like a sphere. Again, it's very easy to imagine. Negatively curved universe is extremely difficult to imagine. The more we try to imagine it, the more we get it wrong. It kind of looks like the saddle of a horse locally.
Right.
I'm not going to attempt to draw the saddle of a horse. But that's just the local description of a negatively curved universe. It doesn't look like that globally. It looks like more like your loofah, the one that you use in the bath.
Yeah. So when I sometimes look for images on Google Images, if I search shape of the universe or something, there's these weird sponge-looking shapes. It's like that's a
negatively curved universe, most likely. And we have a very neat way of understanding it locally. Like if I were to just look at a very small region, like around this point, it would look like a horse's saddle. But we don't just look at the universe at a point. Usually we're interested in what's happening around larger. And then it starts looking a bit difficult to comprehend. Thankfully, we don't live in a negatively curved universe. There are a whole brand of theories called ADS-CFT, which came from string theory and has now inspired the holography paradigm, that talk entirely about these negatively curved universes. Unfortunately, and they have some beautiful relationships there, which is again a paradigm. We don't live in such a universe. We live in this one.
Positively curved.
Yes, so positively curved, eventually tending to flat.
Right.
So the universe we're in today is rather flat, but at very early times it was expanding super rapidly, so transition from being positively curved to a flat universe. Okay, so that's the thing here. So this is only supposed to encode the homogeneity and the isotropy of the universe.
And it encodes that independently of the curvature, or is that?
Yes, so the curvature is parameterized by this k.
Oh yeah.
So depending on if you set this to 0 or 1 or -1, you would get the But overall, it's quite beautiful.
Cool.
Now you can do some math, you can reparameterize it, and you can say, okay, I'm interested only in one direction, the radial direction of the universe. And then the metric starts to look nice. It looks like this. Oh, sorry. The most important thing is you have this scale factor, which is missing here.
Right.
You don't have the scale factor. Einstein's equations allow you to have a scale factor. What this means is the universe can expand or contract. So you can have a universe that goes so that's the important thing here, and it still obeys homogeneity and isotropy. An expanding balloon, if it was homogeneous to start with, why should it be any less homogeneous if it expands? So that's what this encodes. So yes, we just want to look at one direction, and then you can rewrite this as squared p. I'm going to use dr. Some people would call me sloppy, but actually if you do coordinate transforms, this would be something else. But I'm just going to label this r again. It's just a direction that I like to call r. So there's a scale factor which tells you space expands. You can make this even prettier. You can say, okay, I'm going to define a tau, which we call conformal time. I'm just going to take the scale factor out. I'm now going to write it as a function of the conformal time. So my redefinition of time allows me to bring this out. So now this has a neat interpretation. You can think of the scale factor as a clock that slows down as the universe is expanding. Yeah.
Okay.
Yes, so imagine a clock that's ticking slower and slower as the universe expands. So that's the interpretation of this thing.
Right. Okay, so we have our metric that in our universe is slightly positively curved, this k, and then we have this scale factor, which is adding in that the universe can be expanding or contracting.
Yes.
And when it's expanding, we can interpret the scale factor as like this slowing down clock.
Precisely, yeah. So, yeah, without doing anything, there's no quantum mechanics here, it's just general relativity. You've already seen remarkable things. The universe can be flat, it can be positive, it can be negatively curved, and it has the ability to expand or contract. So that's pretty neat. We haven't done any quantum mechanics so far.
And it's still really cool.
It's still really cool. And when quantum mechanics comes in, it becomes cooler. Yes. So I will get rid of this. And I will leave it to the readers to find the beautiful picture.
The beautiful picture of the universe.
Yes. So this is the metric, but we also have, the metric is about the structure of space-time, but we need dynamics. A space-time with just a structure, nothing happening on it, would be boring. And that's why we have the Einstein equations, which is this. And this T mu nu is called the stress energy tensor. It encodes the distribution of matter in the universe. Now, in our homogeneous universe, we only look at stress energy tensors of the form rho, negative p, negative p, negative p. So rho is the energy density of the universe, and all these p's are the pressures in the different directions. They should be the same in an isotropic universe, and the energy density is rho. Yeah. So this is the kind of universe we'll restrict ourselves to.
Right.
When you start putting things in here, it becomes very difficult to solve the Einstein equations.
And does this realistically represent our universe, or
yes, it does for the most part, because the universe is incredibly dilute today. If you have a cube that's about a parsec in each dimension, you will find one hydrogen atom at the center of the cube on average. So this is how dilute our universe is.
Yeah.
That's why I said it's flat today. Yeah.
Right. Okay, so we have a good approximation model for our universe.
Yes.
As isotropic.
Yeah. This is the Friedman metric. This is the Friedman-Robertson-Walker metric. And when you plug this in here, you'll get equations that are called Friedman equations. That I might remember, so let me try to write it down. So we need to define a very special parameter, the Hubble parameter, which is defined like this. It tells us the rate of expansion of the universe relative to the ongoing expansion. So the scale factor, if it's expanding, how fast is the universe expanding, essentially. So the first, there are actually 10 coupled equations that come out from the Einstein equations, but thanks to the simplification we've made, we get only 2, which is amazing.
Nice.
So that would be A dot divided by A, which is the Hubble parameter squared. Something like negative rho would be, or rather positive rho over 3 minus k over A squared. So this is one Friedman equation. If you put this in there, and if you put this there as well, so let's call this one, and the second one is it's even more. It's of course the next derivative, which is how fast does the universe is the universe expanding in an accelerated way. Essentially, I know it's expanding, but is it expanding fast? That's rho plus 3p. So this is the second Friedman equation. Now this encodes how fast the universe is expanding, knowing how much matter exists in the universe and how much pressure that matter is exerting in the universe. Now, to give you a very simple example, if our universe was filled with this hydrogen atom that we saw, and now the universe becomes 2 parsecs in length. It's going to be a large cube, so just leave it. Let's leave it at this.
Yeah.
The density of the universe is going to scale as A over 3, and then the inverse cube of A. And that's because it's matter. If you have one hydrogen atom and the box around it expands, you have one hydrogen atom, it's just your box has cubed in size. Now, if this was light, on the other hand, this would not be negative 3. Do you want to venture a guess?
No.
Okay. This would be 4. And why is that? Because imagine if you have a photon, and the wavelength of the photon was this thing here. Now when your cube expanded, the wavelength of the photon also changed. So you have an extra factor because the wavelength of the photon is being stretched. And
Right.
so that's this thing. So different sources of matter, radiation, normal matter, like hydrogen atoms, they would behave differently as the universe expands.
So intuitively, could we say that as the kind of box of space per photon is increasing, the photons are also becoming lower energy,
Exactly.
and so that's this extra contribution is
Yes.
lower energy as well as fewer photons per given space.
Precisely. And this is similar to the thing that we observed with the Hubble Space Telescope. We saw that distant supernovae were more and more redshifted compared to what we would expect them to be, because we can calculate what frequencies and what luminosity certain stars would be, because we know the nuclear processes that go on inside the star, and we know the mass, we know the luminosity because we can observe it through a telescope. And this redshift, which they did not expect, allowed them to conclude that the universe was expanding. So something like this, instead of seeing a -3, they observed a -4. So you're completely right, is photons becoming less energetic. So this is just for two cases. The matter that we know and love, which is light and hydrogen atoms, but there are other exotic sources of matter, like the cosmological constant, for example, which Einstein included in his equation somewhere here. Actually, it should be on the other side, but excuse me for that. I already put the equal sign. That does not behave like this. That has constant energy density. So it would be scale factor of the order 0. It's very weird. Imagine having a box you're just stretching, and as you stretch, it becomes more and more energetic with some weird matter source or energy source that we've never seen. That's called dark energy. And something like this dark energy is what's going to cause inflation, the inflationary paradigm.
Does this violate energy conservation?
Well, yes. Yes, but maybe in another episode of the podcast we can think of ways of saving that.
Yeah. Yeah, cool.
Yeah, so far so good.
Yeah, so we've covered the way that normal matter scales as the universe expands, the way that light scales, and the way that weird cosmological constant matter scales, which is also known as dark energy.
Yes, and the reason I wrote down these two equations is you can let's put a box on that as well. The reason I wrote this down is because we can actually add these two up and get a relation between the pressure and the matter density. You can remove all the scale factor stuff. That's called the continuity equation. It tells you how pressure would change if energy changed, and you can define a nice parameter called W, which is the ratio of pressure and rho. For radiation, it's 1/3. If you confine a box of light, the energy of the pressure exerted by that radiation will be about 1/3 of the energy in that box. And for matter, it's pressureless, so it's just 0. And for the cosmological constant, this is -1. And there can be like a host of other things in between. So the most general expression, I should not write there. I can write here.
I think it's just about still visible up there, but yeah, maybe here.
I could remove this. So the most general expression for this thing is actually of the form rho is a 1%. And we have a -3 here. Should all work out. So if you put in 1/3, it becomes 4. So you can do this for any source of matter. You can keep varying the W. Now, W being -1 is very alarming. It violates something called the strong energy condition. And that's what we need to cause the universe to expand. I'll try to convince you that there's nothing special about this. It's just a number that changes. And hopefully you're convinced.
Okay.
Yeah?
Yeah.
All right. So we'll get rid of this. So we've never seen anything like this. We've never seen a field with W, omega, whatever you want to call it, equals -1. How do we come up with it then? Well, we have the Friedmann equations. We can propose the existence of a field. Let's say I'm going to write the action of the field, and we'll explain what the action is as well. Cosmology community will kill me for writing it this way. So I will do it like this. We always prefer putting the thing here.
Yeah, right. Gotta keep them happy.
Exactly. Yes, and then we have the metric tensor, which is 5 minus some potential. So this is the field that we're interested in. It also has a mass. So let's call it m squared phi squared. Now, we'll explain all of this. Don't worry. This is a field, phi, which we will introduce to explain where this negative W equals -1 comes from, that's driving the expansion of the universe. And we'll also explore the consequences of putting a hat on this field to make it quantum.
Okay.
Before that, we can go back to something that we know and love in physics, which is a harmonic oscillator. So we'll get rid of this. I'm just going to leave this there. The harmonic oscillator, like we studied this in high school. It's a spring coupled to a mass. And essentially we say the force should be negative kx, which is x is the displacement of the string, and k is a constant that depends on how taut the spring is. Now, we find harmonic oscillators in physics all the time. Anything where the equation of motion is of the form q plus omega squared q equals 0. Anything that satisfies this equation of motion is a harmonic oscillator. And why do we like harmonic oscillators so much? It's because you can take any potential in physics. Let's say you have this weird potential, any potential, and we're interested usually in describing systems around a stable equilibrium. You can take any potential and expand it as a harmonic potential. Why? Because you know the function fx can be written as fx0 plus first derivative of x at x0, x minus x0, so on and so forth. You can do a Taylor expansion. I have to write the second derivative. So this is the Taylor expansion of any function up to the second order. And if a system is in equilibrium, the first derivative is essentially 0 because it's flat. The derivative of the function at this point is x0, sorry. So the only thing left is some constant that we don't care about, and the second derivative of the function looks like this.
Right, so we get harmonic oscillators in any potential. So they're very ambiguous.
Yeah.
Yeah.
In fact, Sidney Coleman, the famous physicist, once said, the career of a young theoretical physicist starts off by quantizing the harmonic oscillator in ever-increasing abstract ways. It's a very important object.
Cool.
And it turns out it's important for us as well. And the solution to this harmonic oscillator, again, nothing quantum, no hats. The solution to the harmonic oscillator is something like this. I'm going to use Q to be consistent. No, sorry, this should not. Let's think of a good variable. omega. So yes, it's quite clear that the exponential function will satisfy this differential equation. And as you know, the most general solution is a linear combination of both individual solutions. So that's great. In a classical harmonic oscillator, you can have 0 as one of the solutions, which means Q equals 0 is a totally valid solution. And that means there's no harmonic oscillator. It's not oscillating, it's just stationary. And then you have these other solutions, which are progressively better. Now, when you quantize it, however, when you demand that Q and P, which is the momentum of the harmonic oscillator, equals I, the Heisenberg quantization, this solution is no longer allowed. You will not have a harmonic oscillator where the ground state energy of the harmonic oscillator is 0. And this is something we've seen in normal quantum mechanics as well. And how do we usually show that? We write down the harmonic oscillator as a function of the creation and annihilation operators, which we introduced earlier. So something like this, you can write your harmonic oscillator like this, barring a few factors of omega and I, which is not relevant for this podcast. And you'll get that the Hamiltonian of your system, which is p squared over 2m, if the mass of the harmonic oscillator has mass, I'm going to consider m equals 1 for simplicity, and q squared over 2, this will become something upon a dagger a plus half. Now this half appears simply because q and p don't commute, which means a and a dagger don't commute. They will be 1, and if you work it all out, you'll see there's this half that always remains. So the ground state energy of the harmonic oscillator is at least 1/2.
Right. Yes, this is unique in quantum mechanics. We find this limit that it can't, its ground state is not 0, its ground state is actually already having some energy.
Yes. And this is extremely important in field theory because our fields are also harmonic oscillators, except they're harmonic oscillators at every single point in space. You can think of a harmonic oscillator at every single point in space, which is this equation. This is nothing but a harmonic oscillator embedded in every single point in space. We can make it easier to digest by saying I'm going to do the Fourier transform. So let's do this here. I can always do a Fourier transform, which is phi x equals phi k e to the, we use positive conventions. So you must have seen this in your math course, and this is the Fourier transform of our field. And if you do the Fourier transform, these derivatives will all just become multiplicative factors of k. You can, for every time you do the derivative of this, you're allowed to bring 1k down, and it just becomes k times that function. And you get these equations, the coupled harmonic oscillators for each mode. So we will call them this, and we will remove this q and make it a phi. And we put a phi here as well. So now what this means is in momentum space, which is a harmonic oscillator for every mode, you have a harmonic oscillator for every single momentum. And each of those harmonic oscillators, oh, I removed it. Each of those harmonic oscillators have a ground state energy. It's not 0. But this solution does not exist in quantum field theory. Now, by virtue of that solution not being allowed, the vacuum is not empty in the sense that it's not the configuration where there's no field. There's always something going on. And that's the thing that allows us to do particle production, for example.
So should we visualize this as every point of the universe is kind of oscillating with this minimum energy, even if it's in the vacuum?
Yes, if you have an empty universe and you say, I have a gravitational field in my empty universe. We don't know how to quantize gravity, but let's assume it's a scalar field. That will not be completely boring. It will have things. For example, And one very good example is the Casimir effect. We'll get rid of this. So imagine we have a box in space, and you put two plates here. Now in the absence of the plate, we've already satisfied ourselves that this box is full of energy of the order omega over 2. That's the energy density. Now the big problem with this that field theorists keep complaining about is, I told you that there's a harmonic oscillator for every momentum. That means you have to integrate it over infinite momenta, which means this thing diverges. And if you have infinite energy in a box, shouldn't that be gravitating? We know that infinite energy should gravitate. The way we cheekily deal with this problem is to say, I'm just going to say this is not accessible. It's just the default state of the universe. I'm going to subtract this ground state energy from every calculation I do, which is called renormalization. Pretend as though. But this matters a lot for the Casimir effect, which can only be explained by the fact that the universe has a ground state energy. Imagine two neutral plates. These are conducting metals, whatever. They're neutral, they're not charged. They're placed in an electromagnetic field, and the electromagnetic field is in its vacuum state. It's not supposed to do anything, right? But actually these plates can attract each other. And that can only be explained because of the vacuum energy. And that's because, remember the solution we had here, for a conducting plate, and let's call this L. For a conducting plate, the boundary conditions dictate that the field should have zero value. You're not supposed to have any electromagnetic field inside a conductor. This is a standard result that we know from high school, even from Gauss's law. So that means you can't have both these modes, because this is a combination of a sine and a cosine. You cannot have a cosine mode here. It means the field has some value. You can only have the sine mode. So solutions like this. It means you need to cut off half of this. And that act of changing the new vacuum state simply by introducing two plates causes a delta. Let's call this, I should not have crossed it out. Let's call this omega k, dq of k. And let's call this the ground state energy of the universe. This delta that's introduced as a result of changing a field configuration is what causes the Casimir effect. And that can be written as Eg when the plates are L apart, subtracted by Eg when the plates are L tends to infinity. So this is the usual ground state energy because the plates are infinitely far away. I'm just going to get this. And now the plates. But this difference is actually what you observe in the laboratory, and people have seen this. The Casimir effect has been shown many times. In fact, people are trying to construct levitating systems with the Casimir effect. It need not always be attractive, it can be repulsive as well if you have certain configurations. So that may be how we levitate one day.
Yeah, nice. So we add these plates in, which force these boundary conditions onto the field, because it forces it to be zero wherever these plates are.
Exactly.
And because there's a restriction in what energy can exist between the plates, can we kind of think of it as now there's kind of a kind of push from the field outside, because there's, or how can we see why that leads to an attraction?
Yes, you could think of it that way. You can say the field wants to be in its lowest possible state. It's telling the plates to get out of the way, and it's pushing them together. There are some other interpretations that say, oh, this could be polarized, because if we take the particle production interpretation, it could be that there are particle pairs being produced, so a negative pair, a positive pair, and a negative pair, a positive pair, and a negative pair, for example. And this negative guy is attracting the positive guy. I don't like this explanation because it's this is far more elegant. It actually tells you what the problem is. It's that the vacuum energy is finite, it's not zero. But you can think of it this way if you like as well.
So from here, the vacuum energy being finite
So vacuum energy is not finite, but if you put it in a box, the reason it's not finite is because it's infinite space. But if you try to put it in a box, you can try to and regularize it. You can say nothing more than the Planck energy is not allowed. Anything more than Planck energy is not allowed. The 10 to the 19 I wrote, that could be the number. Then it has finite energy density. This is why people like to remove this. They don't like it. It creates all sorts of problems, but it's actually important for the Casimir effect.
Right. Yeah. Cool. So, how can we use these ideas to think about cosmological signatures for gravity? For the quantumness.
Yeah. So, the negative field, the negative energy field that we had there was supposed to lead to the expansion of the universe. Why did we want the universe to expand in the first place? Is because in the CMB, the diagram that I drew here, these two parts of the sky are actually very distant in today's terms. You can think of them being several billion light years apart. So that begs the question, why are they so homogeneous looking? Like, why do the spots here seem so similar to the spots there? How are they in causal contact? We can draw a diagram. So if this were a space-time diagram, you would have, this is the path of light, which is why I have this chalk. So these are geodesics. We can call this t equals 0, and then we can call this today. So if you were to, and this is the light that we see, so this is T recombination, which basically means all the hydrogen, all the electrons and protons in the universe combined to form the hydrogen atom. And when they did that, they released light. And that's the light we see, the CMB. So the CMB was born here.
Right.
And this can be the Big Bang, if you like. Now, when all of this light was created, if you trace back these paths, these 45-degree lines are what light can travel, the only region of the universe that's allowed to be in causal contact is this. And this is a result we know from relativity. Anything outside this light cone, this is not in causal contact with Q, for example, which is inside the light cone. For things to be in causal contact, they must be in the same light cone. So none of these things, so this thing is not in causal contact with this, which means this patch should have never known about this patch. Why do they look the same? Is it some random initial condition where someone mysteriously said that everything along this horizontal line must be the same? Well, hopefully the answer is no. We could try to extend these light cones backward, and for that you need more time. You need time to actually go all the way to negative infinity. And you might be worried that time going to negative infinity, what does that mean? That's why we introduced conformal time, this clock that slows down. So in theory, you can just think of it as a clock that runs so slowly that it feels like infinite time has passed. So that's the meaning of t going to negative infinity here.
Right.
Now it's the expansion of the universe, the extremely rapid expansion of the universe, that makes your clock appear to tick so slow, giving you the perception that infinite time has passed. Well, we were not alive to see this, but giving whatever existed at that time. And now, miraculously, the light cones are in causal contact. So we've established causal contact. This is why we need the universe to expand rapidly, for causal contact to be established.
And is this where the inflation is happening?
Exactly.
That you mentioned earlier.
All of this is inflation. So I said it's a paradigm. The first thing that should raise your eyebrows is this.
Yeah,
t going to
negative infinity time.
Yes. So I've just said, yes, there is this mysterious field with negative omega, and it behaves in such a way that it causes the whole universe to stretch rapidly very quickly clocks start ticking slow,
Yeah.
and the universe is in causal contact.
Right.
Yeah.
So this is where the dark energy, inflation,
Yes.
expansion come together
Yeah.
and give an explanation for the homogeneity of parts of the universe that
Yes.
can't have been in causal contact by kind of standard expansion.
Exactly.
They need this super expansion with
Exactly.
weird properties of negative time.
Exactly. And now the universe has expanded so fast between
Mhm.
0 and negative infinity that the edges of the universe are expanding faster than light itself. Better than that, like even some local patches are expanding faster than light can travel. So what that means is the universe expanding so fast is actually shrinking your horizon. The horizon is what you can see today. So if I look in whatever direction in the sky, the farthest star I can see is my cosmological horizon. I'm not going to be able to see that star tomorrow because my horizon has shrunk. The universe is expanding. That star has been pushed out of my field of view. That's what happened. That's what happens in the early universe. So we're saying, these two people, these two galaxies are spots in the CMB, used to be in causal contact. They were pushed out of the horizon. They were in causal contact like way before, but they were pushed out of causal contact at time t0. So you can see they've been pushed out of causal contact. And it gives us the illusion that they've never been in causal contact, but actually if you assume a period of accelerated expansion, they were in causal contact early on. So the sole reason, one of the biggest reasons we invented inflation was to save this, because we didn't want this to be a fine-tuning problem, to say the initial condition of the universe must be the same across the whole sky. Now you can start off with any initial condition here, and it will always converge to this, because the universe expands. It's like an ant moving on a balloon. As you blow in the balloon, the ant is going to see its local region more and more homogeneous, regardless of how the balloon looked before it was inflated.
Cool. And what's the role of quantum mechanics?
Yes, so now comes the interesting part. None of this needed quantum mechanics, but when you put a hat on this, which is what we're going to do, we need to introduce commutation relations again. So that means phi pi. This is equal to I, let's say, for a position. Pi here is the conjugate momentum of the field. So if you think of this as position, this is something like momentum. They don't commute. And we need this. So for quantum mechanics, non-commutativity is the key. And that's why the authors of the BMV experiment, Vlatko, Chiara, Bose, they say if you need to observe a field as quantum, you need to be able to measure both non-commuting degrees of freedom, phi as well as pi. Unfortunately, what happens when the universe expands is pi decays exponentially. It's not that it doesn't exist, it's just that the dynamics of the universe are so intense that it causes this mode to decay. And we can model that very simply. I left this here for a reason. When the universe expands, it's as though this harmonic oscillator that we had in the beginning is time dependent now. It picks up time dependence. And that means it's no longer so easy to solve this like this anymore. Yes, so a simple example would be, I can have time and omega, and let's imagine an omega that looks like this. So it's relatively constant here, omega 2, and here it's omega 1. So this part is easy, it looks constant here, it'll look like this. This part is also roughly constant, so it'll look like this, but I don't know what's happening here in between. We know the solution here, but we don't know what's happening in between. Clearly something's happening between, but because the frequencies are not the same. So what this means is the thing that you call vacuum here, which is how you define the creation and annihilation operators, is different from the thing that you call vacuum here. So the vacuum itself, the notion of what it means to be vacuum, changes as the universe expands.
That's very weird. But
this is
kind
profound.
of cool. That the vacuum is actually physically changing.
Yes, and a very simple way to think about this is if we remember that there's a reason why I drew it like this. If we go back to the time-independent Schrödinger equation that we solved in our first quantum mechanics course, there was this particle hitting a barrier sort of experiment, where the particle was encountering a potential, which is very high. The kinetic energy it had was much lower than the potential, so it couldn't, classically speaking, it can't cross the barrier. But quantum mechanically, there's a certain probability that it can cross the barrier, and that's what we call tunneling. It's possible for this particle to tunnel. The same way, classically speaking, if a particle tries to cross the barrier and it has much higher energy, it would cross the barrier always. But quantum mechanically, there's a probability that the particle gets reflected back. And this is what it means to not be in the same vacuum. This is very similar. The equations are very similar. Because in the time-independent Schrodinger equation, you would have something like b squared psi over dx squared, minus v of psi equals 0, right? This would be the time-independent Schrodinger equation describing this potential. These look the same, right? And actually, you can draw a parallel between that. The non-zero reflectivity of this particle that goes this way, there's a certain probability for it to come back. That's what it means for particles of the type A to be here. Even though this is in vacuum with respect to B, it's not in vacuum with respect to A. So there can be particles of type A here, or particles of, as far as the A operator is concerned, it looks like there are particles here.
So how do we understand this in terms of the tunneling idea? Is that so here we had a vacuum where excitations would be particles A.
Yes.
And here it would be particles of B.
Exactly.
But if we have this A dagger 0 in this region, then...
Yeah, so let's just think of this, let's not do any math, let's just think there are like many A particles there. You would expect that when this changes, which means a barrier has been encountered, all the A particles would be destroyed. We don't talk about A particles anymore, we only talk about B particles or vacuum, whatever the new vacuum is.
Yeah.
But no, in fact, there are some A particles that have managed to cross, jump.
In this tunneling type way.
So it's a very loose analogy. This is just an analogy. It's not how nature works.
Yeah.
But it can help us understand why these two things are related. They have similar mathematical structures. It's a derivative in space. It's a derivative in time. That's the only difference. And you can have some particles here, even though you expect no particles of A to be there.
Right.
Yeah, and that's the beauty of curved space-time. It happens because the metric tensor here couples to the field, and if you do the Fourier transformation as I did, you will get an equation that looks like the parametric harmonic oscillator, which tells you that there will be particle production. The notion of vacuum differs as time advances and as the universe expands, as inflation happens.
Right, so these are particles kind of created by the expansion of space-time.
Yes, you can think of it absolutely like that. The very precise way of saying it would be that there's a non-zero probability, a non-zero occupancy of particle A type in vacuum B.
And these are something that emerges in the quantum.
Yes, this happens only when you put hats on this. So you need the commutation relations. You need A dagger A to be 1.
Yeah.
B dagger B.
So seeing these particles would be is like a unique prediction of quantum space-time.
Yes, and this is in fact quantum field theory in classical space-time. Still we still have the field as being quantum. It's not gravity itself. I haven't put a hat on this yet. We don't know what it means to do that.
Yeah.
But the goal of inflation is actually to say, okay, now that we're prepared to accept that this field gives us the energy that you need for the universe to expand. Why does it do that? The inflation has a potential, let's say, something like this. The field starts off here and it slowly rolls down. As it rolls down, its kinetic energy starts building up. So you can think of a little ball starting very high and rolling down. This omega that we defined here for inflation is actually phi dot squared minus v phi divided by phi dot squared. I'm thinking about the plus. Yeah, so this is actually what it is for inflation. As this moves down, the kinetic energy becomes very large, and the kinetic energy becomes very large. So this term becomes a lot more. It was indeed this. Yes. Let me just make it a lot clearer. So just take me at face value and I say phi omega is defined like this for the scalar field. You can derive all of this. As the field rolls down, the kinetic energy of the field increases. So this becomes less and less negative. Here the potential energy was very high. So it was something -1 or worse, even less than -1. It gave you all the resources you needed to expand. But once it starts rolling down, it tapers off. It doesn't expand anymore because the kinetic energy is caught up. It's no longer expanding. So that's how we control the expansion of the universe. And we need a field to do this because the field can take values that go from this very high value to low values, and it can behave in response to this potential. Now when you quantize it, the field has perturbations. It can vary between these two, between the left and the right, whatever you want to call it. Mm-hmm. And this is the thing that we eventually end up quantizing. When we say we put a hat on phi, what it means is to say that there's a background, and the perturbation is the one that's being quantized. And this is a perturbed quantum field theory in curved spacetime. You have a delta phi dot and delta pi hat, and these two things don't commute. You have I, and you have the whole machinery of quantum field theory in spacetime. The goal now is to say, is this really quantum? Can we see? Mm-hmm. And it's great that this is quantum, that this thing is perturbed, and it gives rise to all the structure in the universe. This is eventually going to be the structure in the universe. But how can we really tell that it's quantum? Mm-hmm. And by extension, what does that mean for gravity?
Mm-hmm. Yeah.
So we saw that, I'm going to call this scales, which we denote by k. A larger k's mean greater momentum.
Okay.
Larger k's mean more wavelength, so longer distances, mm-hmm. and shorter k means less distance. And I have already established that because the universe expanded, the horizon, the Hubble radius, which is what we observe, our cosmological horizon shrinks. So this is the Hubble radius. So as inflation happens, this thing is shrinking, mm-hmm. and when, let's say this is t0 and this is t negative infinity, we're totally okay saying negative infinity now.
Yeah, fine. Yeah. Sure.
And this is somewhere today, let's say. Now these scales that lived in the horizon, mm-hmm. They exit the horizon at different points in time.
Right.
Yeah.
Yeah.
So the shorter scale always exits later, and the longer scale exits first. You can think of it again as a box. Let's say this was the maximum possible wavelength the box was able to accommodate. Mm-hmm. The moment the box shrunk a little bit, it can no longer accommodate this anymore.
Yeah.
So larger scales leave the horizon first, and smaller scales leave the horizon later.
Uh-huh. So these are the large scales that leave... No, sorry.
These are the small scales.
These are the larger scales.
Yeah.
Yeah, higher up on those axes.
Yeah. So
that leave first.
Okay.
Because they kind of don't fit in the space anymore.
Yes.
And right.
So they literally stop oscillating. So
mm-hmm.
the solutions that you saw here,
yeah,
they were actually oscillating solutions.
Mm-hmm.
The field was happily oscillating inside the horizon. But now the horizon has outstripped the size of the field. It means that the fields can no longer oscillate. So they're kind of preserved They're just frozen at whatever state they left the horizon.
Right.
They're frozen at that state.
Right.
And then they re-entered the horizon and they started oscillating again. But this is no longer the same universe that was here.
Yeah.
A lot of time has passed and now we have photons. Somewhere here the CMB was formed. We have photons. The photon picks up, the photon reacts to whatever it is coming into the universe, which is actually a gravitational potential. This field couples to gravity. I took the thing out, but we all remember there's a G mu nu. So this field is coupling to gravity. When you do cosmological perturbation theory, you will see that this is practically indistinguishable from gravity. In fact, some people say that if you quantize gravity, whatever it is that you call the graviton is the thing that will drive inflation. So that's an interesting thought to hold in mind. So when this scale comes back into the horizon, the photon is experiencing gravitational potentials. So the perturbations that we saw here, delta phi, which were really, really small when they started off here, have been stretched to superhorizon scales. Now they've been really stretched, and they can be imprinted across the entire horizon. So what that means is a universe that started off quite small has now become this big, and the perturbations that look like this, let's say like this, has now become like this.
Right.
Same thing.
Yeah.
And the photons are reacting to the potential. So wherever the field depresses a lot, the photon needs to spend a lot more energy climbing out of that well, which means it becomes redshifted. The photon becomes redder. So that's how we see red spots in the sky. If the well is much, it's less deep, then it won't be as redshifted. And then you see bluer spots in the sky. And that's what we observe in the CMB. We see all of those random perturbations that were seeded through quantum mechanics, stretched on superhorizon scales, and the photons that were formed in the universe much later responding to the modes that re-enter the horizon. So this is why we're very excited, because we get structure formation, galaxies, galaxy clusters, the CMB, potentially dark matter. We don't even know what that is today. All of this for free, just by putting a hat. And the problem that we wanted to solve was something else. It was a horizon problem. But if we wanted to explain why the universe was homogeneous, instead we found a mechanism to explain why the universe has structure. And now the skeptic would say, okay, how can you really prove to me that this is quantum?
Yeah.
We're stuck. We don't know how to do this, but there are a couple of proposals and there are a couple of difficulties. So let's walk through that. The first idea is, why don't we do a Bell inequality? Just to quickly recap what a Bell inequality is. We have two people, Alice and Bob, and they each have part of an entangled qubit. They can measure observables A1, A2, B1, B2, and we do the expectation value, the CHSH Bell inequality, for example. You know this better than me, Maria, so if I miss a minus sign, let me know.
We can let the audience error correct if we've missed some signs. But
so, yes, I think this is it, and this should be less than 2 for a Bell inequality. Whereas in quantum mechanics, we see that it can go all the way to 2 root 2. So let's say it's saturated by 2 root 2 if it's a completely entangled state. So can we do a Bell inequality? Does the universe generate entangled states for us? Let's go back to this. Can you think of something entangled coming out from here? No, not yet, because there's only like one type of particle. There's no distinguishability, nothing. So we don't have a notion of two systems yet. But if we had another field, let's say the field C, then we could have another field. So we would have C, and then we would have D. Right? These are the creation operators corresponding to a totally different field. Now, we have the notion of two systems. Let's call this phi 1, phi 2, and again phi 1, phi 2. Initially, they start off in their vacuum state. this is how they are. We're happy. But now, as they evolve, it's no longer in the A vacuum state and the C vacuum state. It picks up some terms. This should actually be an integral because I've told you there are infinitely many modes, but let's just keep it as a sum for now. And there are normalization factors which we will ignore. So going from here to here, the new vacuum actually looks like this, right? The new vacuum here is the 0 of D times the 0 of D, right? This is the new vacuum.
Yeah.
But in the AC picture, it looks like this. This is an entangled state as far as this is concerned. So that's one way to get entanglement. Can we look at multiple fields? And maybe there is a way to generate entanglement between particles of those multiple fields.
Right.
Yeah.
Yeah. So now that we have so before we had one field changing as the vacuum changed. Now we have two, and if you look at the effect of that on the vacuum state, it's actually that it creates entanglement. So we have this situation where the expansion of the universe is actually creating entanglement between multiple fields.
Yes. Yeah. Exactly. And can we use that to do a Bell inequality? I don't know. We're trying. So far, all successful models of inflation have boiled down to single field models, or what we call quasi-single field models. We've never had to use two fields, because if you use two fields, and you can do some math to say it all boils down to having one field or a quasi-single field. But that doesn't preclude the existence of multi-field inflation models. It could be that there are multiple, and then they get entangled. So that's one way. The other way is, okay, let's stop thinking about that for a moment. Let's go back to this picture. Can we use one of these guys to detect the other? Yeah. So let's call this a detector, and let's call this the system. Yes. So the system has to be long wavelength, because in the Bell protocol we have Alice and Bob who are spatially separated, and the detectors are local. So if Alice had a detector, she would be positioning the detector here, and the extent of the detector would be this much. And if Bob had a detector, he would be positioning it here, and the extent of the detector would be this much. So this could mean that a short wavelength mode, the one that was still happily oscillating, could serve as a detector for the long wavelength mode. But the problem with that, as I mentioned in our non-mathematical version, is when the system leaves the horizon, it's no longer quantum, because the solution of this differential equation for the system implies that it comes with a growing part and a decaying part. So the growing part is what's frozen in the horizon, and the decaying part has decayed. So it's the second solution that could solve this differential equation has just decayed away. Now, if that's decayed away, it means we no longer have two non-commuting observables. We need phi and pi to do Bell inequalities.
But pi has decayed.
Yes. So, and if I tell you the solution of phi is something like C, which is a constant, the growing mode, we call it the growing mode, but it should really be called the constant mode. This is how it looks. This is the solution if you solve all of that, all of those equations that I put down there. It's a growing part and a decaying part, and pi is usually like a derivative of, not strictly speaking, but it's a derivative of phi. So you can just think of it as being directly proportional to the decaying mode, right? The constant mode is just 0. So this pi, the conjugate momentum, is entirely dependent on the decaying mode, and it has decayed away. So this is not quantum anymore. It's classical. Well, it looks classical. It is quantum, but
because we can only see one of the
yes.
non-commuting degrees of freedom
Exactly.
being significant.
And that was what we discussed when we said the BMV experiment. We need to have two non-commuting degrees of freedom to observe quantumness. So that's the first problem. This guy is more classical than the detector. The detector with shorter wavelengths oscillates for much longer. It doesn't do this solution, it does the oscillating solution, which is a to the e pi kx b e minus k. So it's happily oscillating. You have both modes. You can do the conjugate momentum. Maybe you could do a Bell inequality. But this the longer wavelength that you're trying to measure has left the horizon. So your detector is more quantum than the system itself, which has never happened in the laboratory. I don't think we ever use.
It's a strange flip of trying to use a detector to detect quantum stuff to actually your detector being the quantum, the more quantum thing.
So that's a huge problem that we've not been able to solve. There are proposals that we have, which is let's use other fields, auxiliary fields. Let's couple it to a detector that's not the same, a mode of the same field, but a different field. And all of these exist for you to read, and I can send some links.
Please do.
Which you can put on the comments. And the other thing is, if you can measure only one non-commuting observable, you're showing nothing. You cannot do a Bell inequality. So an alternative proposal would be to think of a temporal Bell inequality, not a spatial Bell inequality. Can we measure the system twice, the same system twice, instead of measuring two different systems at the same time? Why does this work? If you imagine a qubit and I'm measuring sigma x, let's say, I think this is sigma x, and I also want to measure sigma z on this qubit, which is this, I can go ahead and do that. It's completely fine. Or I could say, I can only measure sigma x, I have no other choice, and I let my qubit evolve. I let it rotate such that sigma x looks like sigma z for the new qubit. So this used to be sigma z before. Now the qubit is rotated, so sigma x looks like sigma z for the new qubit. So that's how you do temporal Bell inequalities, Leggett and Garg have done Leggett-Garg inequalities, for example, where you let the unitary dynamics of your field do the rotation for you, which can give you the setup for temporal Bell inequality. And this is a proposal we've been thinking about for years now, and maybe we're very close to writing something on it.
Cool.
Which is, why don't you consider this field to have exited the horizon? Fine. This other mode also underwent the same unitary evolution. It evolved for a bit longer. So the moment it left here, if you measured phi here, you're measuring a rotated version of that phi, albeit for a different mode. So that's the subtlety here. In our qubit example, we said I will measure the same qubit. Here you're measuring two different modes at different times. So we need to be able to reconcile that. And then you're saying, okay, the unitary allowed me to rotate the thing I'm measuring. So that's how I get my complementary observable. So this is a temporal way to do the same Bell inequality. And that's what we're working on today.
Cool. Yeah, it's very exciting to have another way of trying to get around these problems where the
detector is more quantum than the system.
And it's kind of evading the possibility of doing this kind of experiment, but then with this temporal way, you could actually use the evolution in time to do the Bell inequality experiment.
And in a way it helps us as well, because for the spatial Bell inequality, you need two systems, right? Alice needs to have a qubit, Bob needs to have a qubit. We have one universe. Where is the second system? The universe measured the entire thing at once. And then some people argue, they say, oh, remember that thing where we said these two patches are actually very far apart today? And you can consider them as being separate measurements. You can consider this as being Alice's patch and this being Bob's patch. And sure, there are some contrived models where you can say, yes, you can treat this as one measurement and this as another measurement, and they're space-like separated, so it's an Alice and Bob. So that's what you would do spatially. But temporally, you're using different Fourier modes, which doesn't surprise you. They're equivalent to each other from that perspective.
So it's kind of more natural in a way to do it this way?
I think so. And It's because we have one variable, we have one universe, we have one detector. We don't have the copy as we would in the lab, which is why it's very difficult to do a Bell test in cosmology.
Yeah, very cool.
Yeah.
Cool. So I think we've covered a lot of different cool things.
Yes.
Here. So maybe you can do a kind of recap of what we've covered to summarize. So overall, we've kind of gone through these low energy signatures of quantum gravity and proposals for experiments, and then these like high energy. So the low energy ones were these kind of tabletop experiment proposals, putting masses in superpositions type stuff, and then there are these high energy proposals which are kind of looking at cosmology, the universe as a whole. And in the low energy case, you started by explaining this BMV experiment, which is...
we could quickly draw it as well.
Yeah.
Yes, so this.
So that one is kind of explaining, kind of advancing this idea that Feynman proposed of putting a mass in superposition doing interference, but instead using two masses so that we can actually show possible quantum properties of gravity in mediating an interaction, in creating entanglement between masses.
Yes.
So we put two masses in superposition to then see if entanglement is created by then interfering.
Mm-hmm.
And then you explained a kind of follow-on extension of this, which was the Bose-Einstein condensate version of this, which is using this macroscopic quantum system, the Bose-Einstein condensate, and then considering the gravity of all those particles, the effect of that on the matter, and then you get this interaction of the matter with the gravitational field.
Yes.
And you can also look for signatures of the quantum effects in a similar way. And then we shifted to this high energy regime of thinking about the universe as a whole, and you told us about this problem where different patches of the universe look the same, but they haven't had time to interact to look the same according to what we know about causation in special relativity.
Yes.
And then you explained how the theory of inflation was introduced, or this paradigm was introduced to explain this problem by going back to minus infinity time, and then saying there was this rapid expansion of the universe, faster than light expansion, and that explains this homogeneity.
Yeah.
But then when you treat gravity as a quantum field in this context, then you manage to explain the you end up with this situation of having particles appearing from the vacuum during the expansion of the universe, and using this change of the vacuum over time as the universe is expanding, you can then potentially see this like creation of entanglement between fields, which would actually be a signature of gravity being quantum from this cosmological scale. And then there's this other approach that you would talk about with the modes of the system and detector. Maybe you can summarize that again. I'm not sure.
Yeah. So there we discussed that the field was nothing but a collection of harmonic oscillators, and we wanted to use one harmonic oscillator, which is one mode, to measure the other. And in order to keep the measurements local, we need to use a small mode, and the small mode so happens to be more quantum than the large mode because of this thing. The large mode exits the horizon first, and the small mode exits the horizon later. So when it exits the horizon, this starts being more classical than this. So unfortunately, the detector is more quantum than the system itself, which has never happened before in the laboratory, as far as we know.
But what you're thinking about in your active research is to think of doing a temporal Bell experiment in this scenario, so then you can just use one
Yes.
system that does display these quantum properties.
Yes, that's the hope. So you would just, you're happy measuring this and this, but at different times. And hopefully there's a way to reconcile that with the spatial Bell inequalities that you would otherwise do if you had a lab.
Mm.
Yeah.
Cool. And just to remind me as well, what is the problems in this context that were solved by turning the gravitational field quantum? So we saw that the homogeneity stuff with inflation could be explained with the classical gravitational field.
Yes. And some people would even argue that you don't need quantum gravity for inflation. You just need a quantum inflaton and classical gravity. But as we saw, when you have QFT in curved spacetime, the metric appears in every single thing you do. So if I write the kinetic term for the field, it involves something to do with the metric. When I do perturbation theory, gravity couples to the field. And at that point, it's very hard to say this is gravity and this is inflation. In fact, people have suggested that maybe a complete theory of gravity would give rise to a mechanism of inflation without the inflaton. You can just do it with the gravitational field. So the idea there is gravity and inflation are inexorably linked. That it's just hard to tell one apart from the other. So proving that the inflaton, which is this field, is quantum could be a major step towards saying that gravity itself is also quantum.
Right. Cool.
Yeah.
Yeah, well, I think my brain is now in the shape of the negatively curved universe.
The crochet.
Yeah. But yeah, that was really interesting discussion. It was nice to see concretely these things that we were talking about in the other episode of the different types of experiments to test these quantum aspects of gravity. So yeah, that was really interesting. Thank you for the discussion.
Thank you very much for the invite. Yeah.
And thanks to our audience for joining us. Do check the description where I'll put some links to resources for more reading on these things. And yeah, thanks.
Thank you very much.
Any final words, Aditya, for the audience?
Keep trying. We'll prove that gravity is quantum eventually.
Yeah. Great. Okay. Well, thank you very much.
Thank you.
Bye.
Bye.
Woo.
The universe is big. It's really big.
I just noticed this flashing. Did that?
Oh, it really feels like quantum mechanics.
Yeah, I don't know what happened.
It's a lot of chalk.